Started.
Hi, okay, so welcome to Epoch Week. So we'll just talk about, again, let's just do a brief on how machines learn to see. With an image, when you put it into a computer, what do we have? We just have pixels of ones and zeros, or like from 0 to 256. So when you want to identify an image, what do you want? You want edges, right? So what do we do for edges? We use convolutions. Now, what was the first model that we came up with? AliNet. So do you guys remember why AliNet was used? Like, what was the main big thing in AliNet? Anyone? Okay, fine. So AliNet had backpropagation with CNNs, right? With convolutional networks. So this helps the model learn what it's looking at. Now, moving on from AliNet, we came across AlexNet. Now, do you guys know what the big thing about AlexNet was?
Scaling up.
Yeah, scaling up. Why is that good?
You have like more layers of processing.
Okay, so why would that help? So you have more things to learn. So you have more parameters that you can learn that can actually be used to like identify different images. So that was your AlexNet. Now moving on, we came to BGG. Now what was the thing about BGG?
Stack convolution.
Yeah. So now why are stacks useful?
They change the receptor field of current.
Yeah.
Make
So
it better.
it makes it bigger, essentially better. Yeah. Now coming to ResNet. So with AlexNet, our biggest thing was bigger is better, right? Like the bigger, like a bigger model gave you better results. Now, but with BGG, we had bigger models plus blocks. So this caused like huge number of layers. So what was the thing with ResNet? How did that fix this issue?
The inputs got added. Like,
Yeah.
over stacks of processing
Yeah.
stacks.
So that's how ResNet helped. Now moving on from ResNet. Okay, there's supposed to be a transformer. Forgot to put the image of a transformer. But yeah. So Google had a lot of money and decided to put slap a transformer model on image classification because it performs good. Yeah. So this caused huge parameter. Like, for a transformer to train on images, it requires a lot of parameters. So if we were training for over 300 epochs on a 1.5 billion parameter model. Now comparing this to like ResNet. ResNet had like 80 epochs and is training on like 80 million parameters. Just look at the comparison. The difference between the compute power required to train something like ResNet and something like a transformer. It's over 100 times. And at the end of the day, the performance difference was only 4%. So it doesn't really seem like there's a good high effort to value ratio over here. It's like putting in 100 times more study hours just to get a 4% increase in your grade. I don't think any of you would actually do that, right? Essentially. So they want transformers perform better than everybody else, but at what cost? Now, okay, so think about transformers. So when you're training a model, as a person who is training a model to classify something, like perform a particular task, you have some ideas in mind that you would like the model to follow, right? Like, for example, talk about images. Images have, you'd like them, if you're like you're having an image classifier, you'd like them to have a local receptor field, you'd like to have weight sharing, you'd like to have some kind of translation equivalence as well. Now, do transformers do that? Inherently, do they do that? No. That's the thing. So that's why they required so many parameters because they had to learn how to do all of these different processes as well. So they required so many more parameters, they required so much more compute to do so. But, okay, these three things should look familiar to you guys. Which model inherently does all of these? Yeah, convolutional networks do all these. So, why not just get rid of a transformer and try to train a model based on this convolutional networks again. Let's go back to the basics. Because as you can see, like if we can just increase the performance on this without like increasing the parameters by too many, you can actually perform so much better with like a huge like decrease in compute required also. So that's essentially what context is. It's getting transform performance with just C and S. Okay? So, in these two architectures, what similarities can you see between this and this? Like over here, we're taking in a 256 dimensional vector. You're taking it 56, and then it's going to 64, and 64, again 256, and back to 64. Here, you're going from 64 to 256 to 64. So, can you guys see some kind of similarity between this and this? Okay, so over here, it's going from 64 to 256, again 256 to 64. So this structure looks very similar to this structure, right? Does that make sense? Like, can you guys see the similarity? Yeah, no, not just the neural network. We're just talking about the shape, like how the vector is being processed. Like it's okay. So essentially, in both of these situations, like in this and in this, we have, if this is dimension D, we're moving from a D-dimensional part to a 4-dimensional. Again, keeping it 4-dimensional and moving down to D. Can you guys see this structure in this part and like over here? Yeah, so that's the similarity between ResNet and transformer that we'd like to keep. Okay. Now, moving on from that, what differences do you see between these architectures? Like the major differences? Some I spy. Let's say some I spy. Everything's on the board. You guys just have to think. Like, what differences can you see between a ResNet mode and a transformer? You can't read the numbers here, you can just look at the images.
Activation function.
Yes, activation function. So what's the difference? Okay, that's one. And there's something like activation function. That's close. Think about the number or the frequency at which they're appearing.
There it's like twice, there it's once.
Yeah, so essentially in ReLU it comes after every layer, but in transformer it's not necessarily, it's only over here.
Yeah.
So that's a big difference.
You guys didn't point out one thing. What is this layer? What is that layer? It's a 1 cross 1.
256 pixels.
So it's a 1 cross 1 convolution. Now what is a 1 cross 1 convolution? Whoever says this answer gets a total prize. Essentially the same image. Are you sure? So what is your intuition for making it brighter?
Each pixel can increase 1 to 3 or 3 to 1.
So your logic is you have one image.
If the first pixel is 1, we can, if I do a convolution and the kernel is 3, I can maybe.
So it's like multiplying each value by 3. Okay, that is your claim. But this is not what this layer is.
Scaling.
So what is the difference between what you are describing and what that is?
Scaling,
Scaling. What do you mean by scaling?
like when we are multiplying, that will scale, right?
You're scaling the pixel value, but that is not the difference. What is the dimension? What is the size of this kernel?
One thing I want you guys to remember is the number of layers that you have over here might not be 1. Like what you're looking at, like this 1 cross 1 kernel might not be just on a 2D matrix.
Which one of those layers gives the maximum, which is most important?
Do you guys know why I said that? Like why I said it's not going to be 2D?
Infinity RGB is incomplete.
Because you know
It's not just.
In RGB you have like
you have RGB,
Yeah.
but then what happens when you go back to this? Or BGG any of those?
Yeah.
Yeah. So now you started with RGB. So this was what? 224 cross 226 cross 226 cross 3. Then you ended up with 226 cross 224 cross 224 cross 64. So instead of having only 3 colors, now you have in effect 64 feature colors. So do you remember we did a calculation yesterday, number of parameters in a kernel. What was the number of parameters in a convolutional kernel? Do you remember what yesterday's formula was? Huh? Number of channels into width into height. So It is 3 cross 3 cross 65. Correct? So now what is the difference between that kernel that is just increasing the brightness or decreasing the brightness of the image versus the 1 cross 1 kernel in ResNet? How many elements do you have in that 1 cross 1 kernel?
256.
256. Yeah, correct. So now what can the kernel do? Can it only increase brightness? Huh?
Okay, how would it combine feature maps? It's very good.
Pixel, the kernel value will get multiplied by all of them and we'll have
Correct. So it's a
Weighted average.
averaging of the kernel.
it's a weighted average. Someone told weighted average. What does that remind you of?
Like some features in that may have a higher effect in,
Yeah.
so we will give higher weight to that, and like
Correct.
some features don't have higher no have much effect, so we'll
Similar to the cosine similarity classification.
Yeah. So
Okay, now you know it's a weighted sum of sorts, right? So how can you relate that to some other kind of like basic neural net? What does that remind you of? A weighted average. What does that remind you of? Yeah, like any of you, like all of you.
Convolutions to like extract features.
No, so that we have a convolution. We have a 1 cross 1 convolution, right? Now that's going to be a weighted sum of all the features. Now this weighted sum, what does this remind you of?
What happened to that attention when
attention, there was a weighted sum,
This
but I'm
was-
thinking of
We're
something.
talking about basic. Think,
Like
not dot product. Think, it's close. Dot product, huh? What?
Projection. Yes,
Yeah.
projection. Now, where else have you seen a projection layer anywhere? In this basis set?
in NLP, like going from 256 to 260.
Yes, that was a projection, and you also have a projection in MLP. Do you remember what the MLP equation was? Did I write? It is. Does this what is this operation? Huh? Notation. So does rotation? Yes, or you can think of it as a projection as well. You can think of it as a projection as well. So do you see that a 1 cross 1 kernel and this matrix are similar? Okay, I'm making this claim. 1 cross 1 kernel and this projection is similar. Can anyone tell me how?
Like use a value matrix to like increase the dimensions, something like that.
Okay, so can you tell me what did the value matrix project?
Like have all of the eigenvectors in a column.
It took all the eigenvectors of a column, projected to a subspace of those eigenvectors. But what was it projecting?
Basically, once we extract all the features, we want to know how important each feature is and based
Yeah,
on
so
that-
what was the feature in a transformer? What were the vectors in a VAQ? Huh? No, but what was the vector in the
Like similarity.
what is the input? What is the x?
Importance.
Image, flattened image of words.
The flattened image of a patch. Yes, you're taking a patch, and for each patch, you flattened it and got a vector out of it, and that vector you're projecting with a 1 cross 1 kernel. Here, you flattened it out. So think of it. You had a 256 cross 256 image. You reshaped it to get 16 cross 16. So that's 196 comma 16, right? Do you remember? Each patch is 16. Each patch is 16 cross 16. So one vector is 256 dimensions, and you have 16 into 16, 256 such patches. So the tensor that you get is sequence length 256, embedding dimension 256. Correct? Now when you come here, you are taking embedding dimension 256, projecting up 4 times, and then coming back down to 256. Okay? With a 1 cross 1 convolution, what are you doing? Now sequence length was, what was sequence length? How did you get sequence length? Height into width. So now instead of doing height into width, if I just keep it in its original shape, height times width, and what is my 1 cross 1 correlation doing? Each thing I am projecting along the channel dimension. So see, let's think of this. In our individual thing, in a regular kernel, we took a group of pixels that are adjacent together and process them together, right? Now in a 1 cross 1 kernel, you have only one pixel. So do you have any spatial intermixing? No. But what intermixing do you have? Channel feature intermixing. Along the channel dimension, you have intermixing. In MLP, did you have any spatial intermixing? No. What did all the spatial intermixing? Attention. Do you remember attention could copy information from one place to another, could attend to different parts of the image. So attention does all these spatial information mixing, and MLP and attention both can do channel information mixing. Do you remember? This is something which we covered yesterday. Do you remember? Did you get it? MLP is taking embedding dimension, projecting it up to 4D, projecting it down. It is doing nothing to the sequencing, only the embedding dimension is changing. Similarly, 1 cross 1 kernel, it is acting only on one pixel position at a time. It does not have any spatial operation, only channel wise operation. Yes, no, no, yes, no, yes, yes, no. Halfway. Do you want to try explaining the entire idea? Okay. Anyone got it? Did not get it? Or what didn't you get? Tell me.
Can you explain that MLP like embedding mixing?
So let us. So can you tell me what the input shape you were getting? Sequence length, comma D model. Yeah, embedding dimension. Now attention was doing some fancy stuff, QKV, whatever. At the end, it was giving us what? Sequence length cross D model. Correct? Now it went to, because this is a residual string. The shape has to be constant across that. Now what is the input to the sequence length cross D model? Now here what you're doing, you're getting sequence length cross
4D.
4D.
Okay.
So now what happens when you do this matrix multiplication? This is sequence length cross D. This is D cross 4D. So what is the output? Sequence length cross 4D. So it's not changing the sequence length. This is changing only the channel dimension. It is mixing information in the channel dimension. When we have a 1 cross 1 kernel, can it see local pixels? No, it can see only one pixel at a time. But what can it do?
All the features of the pixel
It can mix all the features across all channels. Why? Because it's not just one value that can only do brightness change. It is a stack of values. It can take a linear combination, a sum, a weighted sum of all the weights. It is a projection. Okay. Clear? So you see that this up projection, down projection along channel dimension only. Okay? Here, up projection, down projection along channel dimension only. They are the same. Does it make sense?
So, one-dimensional kernel does down projection.
No, one-dimensional kernel here depends on number of channels, right? This is taking 64 in and is taking 64 dimensions and going to 256. So how will you do that? You take a weighted sum. Like one of those kernels is taking a weighted sum of those 64 entries, and then you have 256 such kernels, right? So now if you stack them, what do you get? You get a matrix of dimension 64 cross 256, D cross 40. Make sense? So you have D cross 40, 40 cross D, D cross 40, 40 cross D. Mixing along channel dimension only, mixing along embedding dimension only. Spatial information untouched, spatial information untouched. Now the analogy is clear? Yes, no, no, yes. Okay.
Yeah, okay. So moving on from that, do you guys see another major difference? Like pops out. The main architectural difference. This has attention, this does not have attention. Yeah, so that's like the biggest architectural change, right? So now when we want to make context, and okay, you know, attention models are basically a superset of convolutions, right? We talked about this yesterday. So now coming from there, since it's already a superset and the initial couple of layers, they all act like convolution layers anyways. Like the initial attention layers, they just act like convolution layers anyways. And since we wanna like cut attention out of the model, why don't we just put a convolution network there instead? So that's the next change we want. Now we have a convolution layer over there. Now we have to decide what the kernel size has to be. How do we decide what the kernel size has to be? Now looking at this image, try classifying it. What do you think this image is? Like where do you think this image is from? Parrot. Everyone says parrot? It's a cat. Okay, so essentially, see, the thing is, it depends on your local receptive field. So now, with only the information of the feathers, you couldn't figure out that it was a cat because you were missing the key piece of information. Key piece of information being the face. Without the face of the cat, you never know it's a cat because it looks like a parrot. Like our brains are just like, so our brains are wired to not be able to like properly classify images without the entire information given, right? Similarly, computers work the same way. So with like smaller receptive fields, with like smaller like local areas that they can cover, they won't be able to like actually characterize the proper image, like you know. So what we want is we want to increase the kernel size. So we start off in ResNet we have kernel size with 3, right? In most of the things the kernel size is 3. So in the convex paper at least, they try to increase the kernel size slowly. They started with 3, they moved on to 5, 7, 9, so on. And they compared performances amongst all of these. Performance kept on increasing till 7 because of this very reason. But post 7, the performance is kind of dipped, like it just stagnated. So they finally decided on using 7 as like the kernel size. So this is basically what a convex model looks like, the basic architecture. Now, okay, coming from this, how do you think the number of like parameters increased from 3 cross 3 to 7 cross 7?
That's good.
Yeah, exactly, sort of something like that. Okay, so similarly, let's talk about how exactly one particular layer would work. Like how convolution layer inside would work. Now we have initially we're supposed to have what? A 3 cross, like let's say k is the kernel size. We had a 3 cross k kernel, and the depth and height like inside would be L1 and L2, like where L1 is like something of this sort, like where if 64 was the initial number of dimensions and 256 is the final number of dimensions, the total number of dimensions would become 64 into 256 into k square, right? Because you'd have like a cuboid and like each one would have its own cuboid, right? So now, to like instead of doing it this way, like let's say this combines information like spatially and amongst the channel too. Let's say we want to separate this. We want to like combine information spatially differently and like amongst the channels separately. So then what would we do? We would essentially keep 2D vectors, we would stack 2D vectors instead of stacking a whole cuboid. Now this would capture information for each layer separately, right? And so this one, it would capture like the spatial information. And then amongst the channels, if you just put a linear layer finally, it convert all this and like you'd get a final like, you'd be able to mix this information over there too, right? So that's exactly what we're doing. And the thing is, we already have this block that performs that exact operation. And like it does all the mixing between the channel information. So we can just like, we don't have to add that as well. So we just have a block of stacked kernels, like 2D kernels that perform this convolution. So that's exactly what we call depthwise convolutions.
So now question for Todkar. How many parameters do you say, how many times fewer parameters does a depthwise separable convolution use in comparison to a regular convolutional kernel? A regular convolutional layer, okay? So you have one layer which is depthwise separable convolution and another layer which is your regular convolution, okay? Suppose your channel dimension is 64 and your kernel size is 3 cross 3 and your output channel size is 256, okay? how many parameters are there for the depth separable? How many parameters are there for the regular convolution? Can you tell me? So regular convolution we did yesterday. Can you and we recap that calculation just now? How many parameters are there for the convolutional layer? 256. Why 256 square? No, it is 64, 256, 3 cross 3. Any answer?
64 by 64 image? Or just
No, number of channels 64, output channels 256.
64 into 256.
64 into 256 into 9. Yes, that is the answer. No, that's still not the rest of it. How many? That is just one. So correct. That's the number of parameters in the convolutional layer. My question was, how many fewer parameters does depth separable convolution use? Okay. So how many parameters in depth separable? So depth separable is stack of 2D filters followed by a linear layer. Can you calculate? Huh? By 64 by?
All the layers will be
No. Can someone tell me the calculation again? Stack of 2D convolutions followed by one linear layer. So what is the
9 into 64 for that.
9 into 64? Yes.
Then for linear projection is 64. What was it like?
64 into 256. So now can you tell me? Can you calculate? So did you follow his argument? You have 64 filters. Each filter has 9 parameters. So you have 9 into 64 in the first part, and then for the linear layer you have 64 into 256. Right? So totally how many parameters? 9 to 64 plus 64 into 256. Now can you divide these two and tell me what the ratio is? What is the initial one? 64 into 256 into 9. Now it is 9 into 64 plus 64 into 256. What's the ratio? Yeah, I mean, unfortunately, no one gets don't try. And you got, I think you got points already.
about 9 times?
Huh?
8.6.
9 times more about.
Approximately 9 times, no?
Yeah, 8.69.
And does it make sense why it takes 9 times fewer parameters? Does it logically make sense?
Yes.
Why? Because you have that kernel dimension. No? Now you have only one linear layer which is just doing 64 into 96. Earlier you had 9 into 64 into 96. The initial part, which is just 9 into 64, is contribute like is much less than 64 into 256. Make sense? Clear? So coming back, why did you even introduce that test?
Yeah, so essentially it was like, so this is what happens in attention in like transformers as well. Like the information amongst spatial information and the channel information, both of them are like processed separately and then together at the very end. So let's talk about the final changes that we did to ResNet to make it more like a swing transformer. Okay, so we had. Okay, so in the beginning, remember, in attention models, it takes patches. Like we don't do convolutions. Like as in the stride isn't one. Like we take independent patches and then we process that. Similarly, like we do that because there's a lot of repetitive information in the original image. Like just because you're missing like one layer every other. Yeah, like if you're missing every other layer, it doesn't really make that big of a difference in information loss. So what we're doing over here also is we're going to be patching information. So there's not going to be any stride, like we're just patching 4, 4, 4. So that's the main big difference between the initial start of ResNet and Convex. And as we go along, swing transformer follows this kind of architectural block structure. Remember from BDT, we wanted to increase the receptive field, right? So here also we want to do the same thing. So we're taking blocks again. And swing transformer uses the ratio of 1:1:3:1 blocks. So in this also, what we're doing is we're putting 3 blocks first, and then 3, 9, and then 3. So it follows that particular ratio. And like we already talked about moving up the depth-wise convolution layer. We talked about increasing kernel size also. Because okay, see, yeah, we'll talk about kernel size. Let's get back to that. So remember we talked about using stacks instead of a whole cuboid for the convolution layers. Now the thing is, this reduces parameters drastically. Okay. Now the issue with reducing parameters is the amount of information it can learn also goes down, right? So what can we do to improve that? Just increase the width, like the number of like layers we have in between. Just increase that. Like we went from like 256, 64 to like 192, 768, and so on. So increasing this width actually helps improve performance as well. And like, okay, so in ReLU, this is a bottleneck, right? But in this is called an inverted bottleneck. Like as in, over here we're starting with a bigger one, then it goes to something small, and then comes back to the bigger dimension. But in this, you're starting with something small, you're getting a bigger dimension tree, you're resulting in something smaller again. So in one case, this is a bottleneck, and that's an inverted bottleneck. So in this, we're changing it from a bottleneck structure to an inverted bottleneck structure. And like there's a few tiny design details that are different too. Like we're replacing ReLU with GeLU. We have fewer activation functions, fewer normalization layers too. And then we substituted all the batch normal layers with linear norm because it works better. And also we have like separate downsampling layers too. So this is the basic architecture of convex, essentially. Let's look about it with like every tiny detail that we changed actually caused a performance change. So in this paper, what they did was they tried making tiny changes to like the ResNet model, and they compared the performance against the base one. So like as you can see with like every tiny thing, there's been a tiny increase in accuracy. So at the end, we ended up with a model that performs better than Swin Transformer, which is crazy because that's using so much compute power to train, and it trains for so long, and with just convolution layers, we're getting a model that performs better. And if you just look at, this is like a proper accuracy comparison between ResNet, Swin, Convex, and like these are the smaller models, and these are like the bigger models too. So Convex performs better than Swin Transformer Large as well. So this just shows that you don't necessarily need transformers to get better performances. You can use the inherent ability of convolutions to actually get models that train on images better. Yeah, and that's, yeah.
Between ResNet and convex, the only difference that I could see in the image was the order of the layers.
What are the layers? As in?
Not the first. Yeah.
Oh, these two.
Between a ResNet and a convex, there is one convolution layer and there are two stack layers. Two layers which interpret between the layers. So why does it change that much? Yes.
Okay, so again, the drastic changes are actually because drastic change in performance is because of a lot of tiny details. Like like I showed in this image, everything caused a tiny increase. Like can you see? It's kind of like an incremental increase. Like small incremental increases caused a huge incremental increase. But coming back to your question, we're just trying to make it transformers working for some reason. We want to get our ResNet models also working in the same way. Like, okay, so back to like the 7x7 stuff. We talked about how the receptive field changed with like, let's talk about that image with the cat image. With the small kernel, you can't see all that information. You're losing out information. But with the 7x7, you're getting more. So that obviously causes a small increase in performance anyways, right?
So what is, apart from the kernel space, what is the major difference between ResNet and convex? ResNet also has like the similar attention mechanism.
So let us make this another question for getting a total, right? So again, your first question. So what are the differences between ResNet and these two? What are the differences that you see? You moved the bottleneck, one, right? Second, what did you do? You reduce the number of activations. Can you tell me? Okay, what is ReLU?
Rectified linear.
0 and then
Yes.
x. So you can think of it as max of x comma 0. If it is 0, if it is negative, the answer is 0. Okay. So if I have a bunch of ReLU layers, in case any of the outputs are 0 and any of the outputs go negative, what will happen? 0. Full 0. So if my filter gives me negative values somewhere in the computation, what will happen to the image?
0,
The image will be 0, completely 0, blank.
Yeah.
Okay, that neuron has died. Okay, it's like as the neuron got stroked, model got stroked. Same thing here, and same thing. Yeah, basically at every convolution, you have a certain number of strokes, dead neurons. Here, what is GELU? Do you know what GELU is? Yeah, it is like what you do. It is not this, it is like a slightly smooth function and doesn't go to 0. Okay. So, not so many strokes, number one, and not everywhere. Okay. There are like two advantages that this setup. So, lesser strokes, but another implication of that is the outputs of these are what? Can you think of that? Do you think out of all the channels, out of all 64 channels, do you expect all 64 to be having some numbers, or do you expect some of them to be 0? What do you expect them to be? Some to be negative?
That means that if I want a cat,
Yeah.
that particular filter makes it's not cat.
It's not detecting something. But here,
It will make it more negative such that it become more to the.
here the thing is you're not getting so many sparsity. You're not getting as many dead neurons. So in the channel dimension, you don't have so many zeros. You have much fewer zeros. This has some impact, but it is not entirely clear to motivate why that has an impact. Sharon, you have this thing now. At the end of the sessions, we'll come back to this point. Okay, so let's keep this thing in mind. A lot of stroke in resonant, no stroke in convex, really no stroke in. You have like the. So what is the equivalent of stroke? In one vector, you have a bunch of zeros. That vector is sparse. What do you think? So what happens when vector is sparse? If you have 64 bases that you can use, you are using only 10 of them at a time. Okay. What's the opposite effect of this? Huh? When you have only 64 bases, you end up using. So the resonant what is doing, you have 64 bases and you're using only 20 at a time. Okay. In transformer you have 64 bases, but you end up what is the opposite of this? What could be the opposite of this?
Superposition.
You somehow use more bases. Now that does not make sense, right?
Superposition.
Because a vector space of dimension d can have only d bases dimension. But transformers somehow represent more than d concepts in d dimensions. Can you think of how you could get away with that? Any clue? Yes. So if vectors are 90 degree,
By putting the features.
so the thing is, if vectors are 90 degree, you have only d dimensions. If every vector is orthogonal to each other, you have only d bases d dimensions. Okay, they are not linearly dependent. If I make it 89 degree, they are linearly dependent but with some loss. Turns out you can do this like when you allow for this slightly lossy kind of orthogonality, you can experiment, you can like start representing almost an exponential number of ideas, nearly perpendicular vectors. So it's like the exact opposite. Like there you had ultra sparse architecture, here you had extra concepts being represented in very small dimensions. So that's why, for example, you can represent millions of, like, you can find one direction that corresponds to Golden Gate Bridge, and you can find one direction corresponding to something else. So in like large language models, in one layer itself, you can probably find like a million unique directions that correspond to a million different concepts. But it's only a 5,000 dimensional vector space. But still you are representing like a million different things. Interesting. Okay, so that's like the exact opposite, and you are able to achieve that because you don't have this stroke creating ReLU every single place. And that is like the impact that these small tiny changes could have.
That makes sense, right? Because suppose I have a model
Yeah.
related to Russia. I don't expect Moscow to be very different from
Yeah, so you find like very drastically different. So you find one vector for Golden Gate Bridge, you find another vector for Trump and stuff like that. And when you increase the like vector for Golden Gate Bridge, you don't increase the Trumpness. The model starts talking about Golden Gate Bridge, things like that. So yeah, they're like somehow distinct also.
Then why did we went for sigmoid in the first place instead of Epoch?
Oh, sigmoid initially. That is because initially there was this model of the neuron called like what? Hodgkin huxley, something like that. And the neuron activation in your brain is like that model was like a sigmoid, and they just ran with it. That's all. Yeah.
No, but that doesn't work very well because the brain operates near criticality, which means it operates near the point where the sigmoid becomes half. So small changes make a reasonably big change. The problem when you make that a neural network is the neural network doesn't necessarily operate near that area. So you lose a lot of information.
So do you see a sigmoid has a linear part of it, no? It's like going from 0 to 1, and when it's near 0, it's almost linear, right? The brain operates in this region, so a small change is making some change. Neural networks decide to operate at the extremes, okay? Either near 0 or near 1. So if you change it, it is 1 is 1 and 0 is 0, nothing big happens. So because of that issue, you want to get rid of those, things becoming very smaller, things becoming very large. You just ditch sigmoid and you go to the loop. Okay? So yeah, so a lot of these very small things have big impact.
Unfortunately, see over here, so you can see over here, we have taken one next step and we have uploaded say some image, and this is the histogram of the values of activations after the last year. So as you can see, 50.83% of the activations are sparse, like they are negative, and all of them will become 0 in the next step because of the like this is the usual sparsity that we have. Say instead of convex net, if we go with lane net, again 57% sparsity. Like here we have the 0 and all of these activations are negative, and all of these will be zeroed out by the value. ResNet also similar. You can see the center itself is the mean of the activation itself somewhere in the left of it. So 72% of the activations are sparse. Like they are going to become zero. Yeah, right. So with that, the first day we went with how machines learn to see. Second day we saw how machines learn to see better. Now we are going to see what machines learn to see in the first place, like what did they learn. So in the first session itself, we said that we can't directly check how has the model learned or not, and so we are relying on the image classification objective. So if the model is able to classify images, okay, I'll assume that it has learned. But now I want to be more sure. How can I be? How can I exactly verify what has the model learned? So there are so many convolution kernels inside. What are those kernels doing exactly? And specifically, because there are multiple layers of kernels. The first layer still we can imagine, okay, there might be edge detector kernels, or say some sharpening kernels or something. But if the kernels are like after 2 or 3 layers, we can't intuitively think what they might be doing, because they are working on the outputs of previous kernels, followed by some non-linearity like ReLU or sigmoid, followed by max pooling or mean pooling. So it's like we can't mathematically go about okay what they might be doing, right? So now coming to now, yeah. Before that, we will do a little bit of theory. So yeah, how many of you know backpropagation? Okay, how many of you know gradient descent but don't know backpropagation? Okay, backpropagation is the same as gradient descent. Type of this. not want it. Right. So, in gradient descent is actually applicable even in problems other than linear regression. In linear regression, we have a specific objective. Okay, I need to find W1, W2 weights which fit my data the best. But even in a general case, you might have some loss function. Say a loss function. So you might have a model which takes some input x, gives and it has some parameters, learnable parameters. Say W, like this W contains all the W1, W2, everything that will be there in the network. And this data will be fed into it and it will give some output y. The loss will be calculated over y and it will be some value. Or maybe like I can write this function as the loss is the function of my input x and the model parameters w, right? And now I want to find the best model parameters w. In this sense, I want this w such that so this prediction y hat, and I have some actual labels y. I want the discrepancy between these two to be the minimum, or that discrepancy is measured by this loss function. So I want this loss function to be minimum. I want w such that for like an average value of x, it should give the minimum loss function possible. And since this function might not be trivial, like usually if you want to minimize something, we can either do like just find the derivatives with respect to each of these wi's, set them to 0, and we are done. But analytically doing that is not feasible when the w is very large. So what we do is gradient descent. So we start with some random w's. Now when I'm writing w, understand that all the w's in the network are considered over here. So there might be this w2, w1, like all of these connections are weights actually in neural nets. All of these are some number. So I'll initialize them randomly, and then at each step I'll replace them with w minus some learning rate. So learning rate is given by theta mostly, or alpha, times the gradient of the loss function with respect to w. Right, this is gradient descent. Okay, anybody here is not familiar with the idea of gradient descent? Okay, gradient descent is something like, say this is a function. Say fx is x square. I want to find its minimum. So now I know that the minimum is 0, but suppose I don't know. I start at this point, say x is equal to 1. What I will do is I will find the gradient. Gradient is the derivative. I will find the derivative at this point. Derivative of this function is 2x. So over here the derivative is 2. Undo 2, so it's positive 2. So now you will move in the opposite direction by scaled by a small learning rate, which is usually 0.1 or 0.00. So you move behind. The gradient is positive, you move behind. Say if you had started over here, the gradient was negative, so you would move ahead. And you will keep on moving. So if you move ahead, you come over here, so somewhere over here. Now again you keep on moving until you reach the minimum. This is the theory behind gradient descent. So what we do is we take the gradient, because gradient is indicative of which direction I have to go. So learning rate is kind of the step size. So here if you take a step of, so here the gradient is 2. If you directly take minus 2, you will get over here, x is equal to minus 1. Over here, again the gradient will be plus 2. You will again come over here and you will keep on jumping. So you want to control the step size, because gradient is, strictly speaking, gradient is only telling you which direction you have to go. How much you need to go is something that you should decide. and that should be scaled by the gradient. So if the gradient is higher, say at x is equal to 2, the gradient is 4. Yeah, the gradient is 4. So you need to move by a larger step than over here. Did somebody ask? So that's why this is a common idea that you subtract the scaled version of the gradient from this weight. Eventually, everything will. So this you do for all weights together. Then you do it again. Then you do it again, and you keep on doing it until you reach a good enough value of this loss. So this loss keeps on decreasing. Finally, it reaches a minimum. So in neural nets also, what happens is, so neural nets. Okay, all convolutional neural networks are also neural nets. So you might have seen yesterday also we wrote them as a function of so f2 of f1 of x plus x, something like this, some complicated function like this. Now it says f1 has the parameters w1, w1. When I am saying it has the parameter of w1, it means that it is using w1 to multiply something, and that w1 is something which needs to be learned. So what you will do is, you will take the derivative of loss with respect to w. So you will use the chain rule, take the derivative of loss with respect to f2, then take the derivative of f2 with respect to f1, take the derivative of f1 with respect to w1, like wherever w1 is being used in this function of f1. And that whole chain of gradients you will multiply together, and that will be this. You will subtract this from every weight, and yeah, that's how you will reach the minimum. Now the interesting part is, this gives us the idea of gradient descent, and that idea extended to form back propagation. Gives us the flexibility to just choose a loss function. So all that you need to do is just give me a loss function. Any complex network you give that has some features, that has some weights, parameters that you need to find which are the best parameters for that network. It will learn them automatically. Just you give the loss function. That's it. Because gradient descent usually works universally. I mean, usually, not always, but for most of for all practical purposes, you will consider that gradient descent always works, and it will always give me the best parameters. So all that I need to do is design a loss function. It will tell me how that loss function is going. Fine. Now coming to the next idea, which is of regularization. Now the interesting part is, so those who know linear regression, this is a very common example. So what you do is, this is your predicted term, and this is the actual label. So you want to train a model to map from x to y. So x is some input, y is some label, and you want to find those labels. So you have this function. So this theta naught plus summation of xi theta I is a function that I have said it is the f1 function, and now I want to find the parameters of these theta. So theta are the parameters over here. I want to find the parameters such that this approximates yi as good as possible. So I want to reduce their difference whole square. Now y squared, I won't go over that over here, but yeah, something like this I want. And this is what we usually do. But say sometimes you want to have some additional constraint. So say you have the additional constraint that all the weights. So what might happen is, say there are two features, x1 and x2. And both of these are highly correlated. So in the sense, if x1 is high, x2 will also be high. If x1 is low, x2 will also be low. In that case, the model might learn something like this. So in that case, say w1 is equal to 2 and W2 is equal to 3 are some valid, are the minimum. Say this is the best parameters that I need to have. So 2x1 plus 3x2 is the best parameterization, the best function that I can get. Now consider this function. So I have something like say 5x1. No wait. Say 12x1 minus 7x2. Now this might look completely different, but since I said x1 and x2 are nearly correlated, so we can assume that okay fine. So if both of their values are nearly the same, what will happen? Both of these will give nearly the same value. Although there might be some differences, because I said this is the best, it will have slightly lower value. But since gradient descent itself is an approximation, we are never guaranteed that you will get the exact global minima to the last decimal point. It's just an approximation. So that approximation might give you this solution also. And what's more, this completely changes the perspective. Here you are thinking that okay, you need to add both the features to get something. Here it is instead saying that you need to subtract the features to get something. So it might harm interpretability also. So here we want to add the constraint that this W1 and W2 themselves should be as small as possible, or at least their magnitude should be as small as possible. Or we can say that W1 square plus W2 square should be as small as possible. So what will this ensure? This will ensure that we don't get stuck over there. Right. So I change my loss function itself. My loss function will have a lambda. Lambda is a scaling parameter that I can control. How much do you want to allow these W1, W2 from becoming big? Lambda times the sum of all the weights square. Right. So what? Okay. Now you can argue that we can have something like mod of W1 plus mod of W2 also. This is also valid. Eventually, what we want to do is we want to modify the loss function such that we want to add additional terms such that some other constraint that we would like the model to follow can be implemented. So now whenever the model will try to minimize this, it will try to minimize both this also, it will try to improve accuracy, it will try to reduce this error also, and it will try to become as simplistic as possible. So it will try to don't go into very high W1, W2, choose a small ones, something like that. And that lambda is a parameter that we will control. So how much do you want to force the model that no, you don't have to use higher parameters? Yes, exactly. So that's why that lambda shouldn't be very high. That lambda should be controlled. Yeah. Finally, okay. So mainly, I don't want to tell you what that this regularization does. I only want to introduce the idea of now you only have to design a loss function, a very good loss function. Whatever you want to do, just design a good loss function, and you will get it. Right. Now coming back to what did the model learn? So feature visualization. So say there are many convolution kernels inside the net. You want to try and find out what is some particular kernel doing. So say somewhere like in the third layer you have some convolution kernel. How will you determine what it is doing? So if it was in the earlier layers, you can still determine, like we saw that if we have something like negative over here, positive over here, 0 over here, or say positive over here. In that case, or maybe it might not be exactly one, but say some positive numbers over here, some negative numbers over here. On just seeing this, we can determine, okay, it is detecting edges, horizontal edges, right? We covered it in the first class when we manually were designing curves. So if we see anything of this sort, we can say, okay, finding the edges. But as we go in the higher layers, these numbers alone will not mean anything. So even if you see such a kernel in a higher layer, it will not give you insights into what exactly it is detecting, because this is going to act, this is going to take input from the previous layer's feature counts. So it's not that straightforward. So how can we visualize? So one simple trick is you take this kernel, like we are anyways going to apply this kernel to all inputs. Now you have a large data set, we have ImageNet, mostly models are trained on ImageNet. So just take some random data set, random pictures from the ImageNet, run them through the network, and for whichever pixels the output of this kernel, for whatever patches of images, the output of this kernel is going to be maximum. We will treat those images separately. So you are getting, so there was some kernel, say some kernel like this inside the neural net. It is going to be applied on some image, not exactly an image, but some patch of image. So somewhere over here there will be a 3x3 patch of the image. This is going to we are going to convolve this matrix over this window, and you will get a single scalar output, right? Say you get 5, then over here you get 0.1, 0.7, something like that. Now whenever you get high outputs, now high is obviously like relative, you can just sort them by the maximum magnitudes, fine. So whenever you get very high magnitudes, it means that this was exactly the input that this feature wanted. Everybody with me? So when this is, say, so if we represent this as a vector, we open this up as a vector, and then now and we open this patch also as a vector, you can see that convolution is nothing but a vector dot product, right? So when we are saying that whenever that dot product is maximum only when both the vectors are in similar directions, right?
Yes. So we are like near the result. We approach the result we expect to.
Yes. So we don't. No, I did not get it.
Like the output of this is like expected like to behave result.
Expected.
As we predicted to happen, the model works like that.
Yeah. So if the input is exactly in the same direction, then this activation will be higher. This output scalar will be higher. Right. So this can be a good measure of what is the model predicting. And the interesting part is you don't need to know what input it was. You can directly see what image it was. So for example, there was some kernel which gave very high activations on these set of images. You can look at it and say, okay, so it might be referring to, say, fans. Or say you can see balls also over there that have strips like this. So maybe it is representing strips. Whenever there are strips, or to be more precise, whenever there are curved strips, this kernel is it is firing over here and it is identifying those. Right? Similarly, over here you can maybe say it's identifying dog faces or snouts. So now here clouds, here towers maybe. But yeah, can somebody point out a limitation of this method? What are we missing? Type of the object.
Like we don't know what it's picking up on. It could be any number of things. Like in the second thing, it might be picking up on 2 eyes and a nose, or it might be picking up on a dog or like something.
So we are not sure what it is picking up on. It might be that it is only picking up on the snouts, and it turns out that in our data set all the snouts are of dogs only. that's why it is showing all the dog images. But it might be possible that it is just representing snouts. Over here it might be that it is just representing say circular points or something. Like it is not representative of what the kernel is actually doing. Right. And everybody agrees, no? The limitation is this, that it is not enough. And hence we do feature visualization by optimization. So yeah, so now what we will do is we will say, okay, so using images from the data set as input and looking at the activations is not giving me what I want. So I will not depend on the data set. I'll make my own data set. I'll make my own images. What does that mean? So again, I want to find inputs that maximize this output, right? Now relating this to what we saw just now, gradient descent. So gradient descent is a method to minimize a loss function. So you have a loss function, you have some input, that input gets converted to a scalar quantity, you define a loss function over that scalar quantity, and if you want to find the best parameters to minimize this loss function, you can do it using gradient descent. Here the problem is same, you only need to maximize the output. So your input is some image, some say 224 plus 224 image is the input. Output is this activation. We are stopping at this particular layer, whatever layer this is. Output is this activation. And the parameters involved. What are the parameters involved? Okay, wait. What is input again? First of all, okay, so parameters are those that I want to optimize. I want to find the best parameters. Here, what I want to find, what do I want to find?
The input.
I want to find the input. I want to find an input image X, which is say a matrix of numbers. I want to find this such that, and what am I given, right? What is fixed?
The weights.
The weights, the kernel weights, the entire neural network is fixed. So these are my parameters. My input is the neural network itself. And what am I trying to, I shouldn't name it loss because I don't want to minimize it, I want to maximize it. Objective to maximize the activation. So whatever you get when this image is passed into the neural network, in this partial neural network, till that convolution layer, right, the activation, right? This I want to maximize. Now for minimizing, you take the gradient, you keep on subtracting. For maximizing, what do you do? Anybody, just speak up. You add, right? So you will take the gradient and instead of subtracting, you will add. So you are not doing gradient descent, you are doing gradient ascent in some sense. Right? Now again, important part. Gradients taken with respect to what? So say I am naming this AI. I will take gradients of AI with respect to X. Each X JK, right? Each of the points inside this matrix, I'll take the gradients. And I'll keep on adding them, trying to maximize this objective, this AI. And I will get some feature visualizations like this. So here it is like kind of more visible. Okay, so the visualization shows only strips, so it is neither baseball nor fans, it is strips. Here we are getting exactly the face of a dog. Like there is a nose, there are eyes also. In fact, there are 4 eyes, the eyes above also. There is fur, so it is probably dog face or animal faces. Here, clouds, we are getting something like this. So, yeah, and over here, towers and sky, we are getting both. It's not only representing towers, it is representing towers in the background of a sky. So, we are able to get better representations, and what is interesting is, this model was never trained to generate images. You never taught this model how to make new images. You made it like a discriminative model, but it turned out to be generative. Like it learned how the images can be created in a way. Right? And you get these kinds of outputs. Any doubt till here?
Let us see whether you guys paid attention. So, why did he even do all of this?
To visualize which images like give a particular output the most.
To visualize what exactly that layer is doing.
So no, I got like so many different answers. You told visualize what the model has done. You told visualize what the layer kernel. So is it visualize what the kernel or the layer or the model? Model is fine.
The kernel.
Kernel?
Right, so okay. Specifically the kernel that means so now you can see more of this over so these are some kinds of edges. So this is okay. So again, this visualization is done on something called the Google Net, Google Net, whatever. And this was one of the contemporaries of VGG mod. So when we saw VGG, in fact, in the challenge where VGG was introduced itself, it had multiple sub problems in that challenge. And in the classification challenge, VGG had come second and GoogleNet had come first. But it uses somewhat curious architecture which we don't see in later models. That's why we did not cover it. But for the time being, we are only concerned it should have a kernel. That's it. If it has a kernel, we can visualize it because gradient descent does not feel anything like if you have residual connections or not. You have a direct, you have ReLU or sigmoid. It does not care. Right. So these are some kinds of features. So in the primitive layers, you can see features like textures are okay. These are edges. These are textures. These are patterns. So you can see as layer moves on, it is able to learn more and more complicated patterns.
So what was the algorithm for detecting a cat on day 1? You guys came up with some algorithm, no? What was your algorithm?
Lines.
First find the
Point the lines.
yeah, eyes and nose and mouth and all that. Eyes and nose and mouth are created by textures. Textures are created by edges and corners, and edges and corners are created by the pixels.
And that's what
Object, eyes and nose and mouth, textures, edges from the pixels. So you came up with an algorithm. Based on that algorithm, heuristically you created some architecture. You ran it, you trained it, and to some extent, it is following what you expect it to do. Very good, right?
okay, right. And just how we start weights randomly initiated. Here also we started with X, which is randomly initiated. So from random noise, this is just noise. And then you start back propagating from that feature. So you slowly, by step 2048, you get such size. Again, this is not how it actually works. We are doing some regularization. I'll come to that. Right, and yeah, now we can actually optimize along multiple things. So you can optimize along a neuron. Now there are channels, right? So multiple neurons are there in a channel. So to remember how how most of these architectures were, there were multiple of these feature maps, like there were multiple kernels, each kernel made a different feature map, and then the next layer's kernel used each of these feature maps. So if there were 96 kernels that made 96 feature maps over here each kernel, so here if there are 128 kernels, each kernel will be of the form of d-dimensional kernel having 96 channels. These are called channels. Everybody follows? We had something like, so because the same kernel cannot go through each and every channel. So like we saw for the first case, when we have RGB images, we have 3 channels, and our kernel will not be a simple 2D matrix but a 3D matrix with the third dimension for channels. Here also you have channels. So either we can optimize for a single feature, a single kernel, single 2D kernel, or we can optimize for the entire channel. So whatever this entire channel is doing, we can optimize. Right? Like whatever this kernel is doing to all the channels, we can visualize. So that is what is shown over here. And now you have multiple such kernels, right? You have 128 kernels over here. You can, so again, how can you visualize all of these together? Because when we are going to do the forward pass, what are we going to do? We are going to convolve the first layer with the first kernel with the first feature map, second kernel with the second feature map, and so on. And then we are going to add them up to a single pixel, right? Like each part will map to a single pixel. Multiple patches will map to an entire new feature space, and all of these 128 together will give us 128 feature spaces. Right? This was something that was happening. So you have a single output. So whenever you have a single output, so again, so coming to a small nuance, each kernel is going to act on the image at all these positions, right? First over here, then over here, then over here, and so on. It's going to slide through. When optimizing, and it is going to give an entire feature. While optimizing, we can optimize only one thing. Like you need to give a scalar output that you need to optimize. So by default, we take the central output. So whatever this kernel took from the central part of the image and projected it into the feature map, that thing we will try and minimize. And that's why you will see most of these are centered around, like the brightness is centered around the center. Right? It's because, okay, we will come to this soon. Fine. And okay, now when we have multiple channels, these multiple channels, so this kernel of 3 dimensions is going to add these together. So again, you are going to have a single output only, and again we can minimize this channel. Now coming to layers. So layer, I was saying we have 128 kernels. Now is the interesting part. All of these are not going to add. All of them are going to stack, right? So this is the first kernel's feature map, then second kernel's feature map, third kernel's feature map, and so on. So now it is not getting added by default. But say I want to minimize the entire, like I want to visualize what entire layer has done. So what I will do is I will simply add them. Like I have no other option. I need to have a scalar loss option. That is for sure. So I will just add all of these together and visualize that. Right? Yeah, and you get something like layer. And this was the idea that, and okay. So either you can add all of them, or you can add them and square and add them. Now again, what's the difference between squaring and directly adding? It's the same as why we use squared for mean squared error and not. So it's just that, see, both of them intuitively speaking, if you just add them directly or if you square and add them, they are going to minimize the same thing. Maximize the same thing. So if you are saying that you want to maximize the output of this layer, either you maximize the output of each neuron. Okay, now I'll refer to the coordinate of the neuron also. So whether you maximize the output of each neuron squared or whether you maximize the sum of all neurons, it's going to be like roughly the same. So in the original paper, so Google released something called Deep Dream, and that used square. And yeah, Deep Dream will come soon. And okay, now you can also minimize class logics. So after this entire image is passed, finally you have neurons that are mapping to classes, right? Housing classes of ImageNet. You can take a class and ask it, okay, if I want to maximize the output for this class, what can I do? Right? And again, it will be just minimization. So my objective will be the output of that class. And the parameters that I want to optimize is the image. So image passing through the whole net giving this, I'll backpropagate throughout the entire network and find the best pixels for that image. That gives this class logics. So maybe this is Fox, I don't know. Yeah, and you can also minimize class probability. So if you all know this, in any classification in general, say you got 10 classes, all of these outputs will be something like, say class 1 you get 5, class 2 you get 10, class 3 you get 0.9, class 4 you get 6. So this is the output of the network, right? It's going to give 10 outputs, 4 outputs. And these 4 outputs are just any real numbers. But you want a probability distribution, right? Wherever we have seen that we gave out a probability distribution. So how do you convert this to probability distribution? You take the softmax function. So you do something. Okay, I remember first day itself I did not go deeper. Fine, I won't go deeper now also.
So we are getting so differences for classes.
Yeah, exactly. So they come to it later. They have a discussion over there. So the thing is, if you want to increase this itself. Now, okay, if I tell you that the logit of 2 is 10, this is called the logit. If this is 10, can you tell what will be the probability?
No.
Why? Like, you need information about the other logits, right? If the other logits are 20, 30, this is nothing, right? So, when you are converting these two probabilities, you are actually combining information from all over there. And now when you say that you want to maximize the class probability, what you can alternatively do is, either you can increase this, either you can increase the activation for this class, or you can decrease the others. So, and that's the kind of thing that the model tries to do. So it's trying to make this look less like trees. It's also trying to make it look more like foxes, but it's trying to make it look less like everything else. And in that whole thing, like, it becomes uninterpretable. So we are not able to identify it. That's the explanation these people give in their paper. Right. So yeah, this is why we need to. Yeah. Now Okay, so now let's see. So yeah, so we trained the four main models that we covered: LayNet, AlexNet, ResNet, and Cord next. Obviously, we are not VIT because we are not that rich. And we trained kind of miniature versions of all of these on CIFAR 10. So CIFAR 10 is a small data set with some 60,000 images and 10 classes. So 10 classes are truck, car, we'll see. So we trained smaller versions of these networks on these. And yeah, so now let's play with them. So first, let's see what they are detecting. So say I am uploading an image of a car. Right, so car is over here. Car is not even third. Yeah, because it's LayNet. LayNet, if you remember, it was the first network. So yeah, acceptable. Yeah, AlexNet is good. It's giving car, like it's giving 70% confidence to car. ResNet is also performing very well. Cord next is also performing well. Fine. Right. Now, yeah, right. Fine. There are different images we will see later. So this is a simple kernel visualization. So let's say we don't want to do a okay, I should have shown this earlier. The first ever idea that we had, we just look at the kernels. These are the kernels. What can you understand? What is this extracting? Like, it makes no sense because first it's 3 cross 3. And yeah, so let's see LayNet. LayNet has 5 cross 5. So 5 cross 5. But what can you understand from this? Like, it makes no sense, right? This was to motivate that this won't work. You need to do feature visualization using optimization. Right, so again, we can visualize anything. Let's say we want to visualize a neuron. We will move till 500 iterations. Let's reduce the learning rate to 0.07. And yeah, regularizations, I will come to it soon. Yeah, let's start from random noise. We selected the first channel, 0 channel. This is what the convolutions are. Like, this is the kernel that was there. So this is the first layer in LayNet. Okay, fine with LayNet now, or do people want better nets? Let's go with AlexNet. Features 0.1 say. And yeah, first channel only, like 0 channel. So you get this, na? It's initially.
You clicked it twice.
So it's initially completely random because we are starting from random noise, so everything is just random. And it made this feature. So yeah, this is what that selected kernel is representing. Okay, tote back question. Yeah. Okay, so first of all, no tote back question. Okay. why is this? No, the second question is tote back. So why is this not interpretable? Why can't you look? Why can't you see any dogs or cats over here?
Because first layer learns the basic features.
Exactly. So this is the first layer. What can you expect from first layer? Right. So that's the reason. Now, an important question. Why is it so small?
It's the center.
Center.
Like, I think this is something.
It is
Okay.
center, but why is it small?
Only kernel size.
Now say I am taking feature 4.
Effect is small.
Now it is giving me a larger. Why?
It's local, synthesizing from center outputs.
Why?
It's
As you go
including
deep.
the local thing
Mac.
as we go further.
What does that mean? What idea? Which idea am I looking for? Like, I'm looking for.
Max.
That is true, but like we saw a bunch of ideas. So over 2 days, we saw a lot of history, and in that, one of those ideas is very important for this. So what is that idea?
Local.
And you want to
See.
feature 6.
Okay, let's look at feature 6. Feature 6 means 6th layer. Okay.
Same size.
Which kernel is
So first you saw layer 1 kernel, and that was very small.
But like there are many kernels for each.
Anyone, one of them. Randomly one of them. Then in layer 4 you saw bigger visualization. In layer 6 you saw an even bigger visualization. So, it's generate. Oh, layer 12. I think the extent issue. It's like gradient descent is not working through.
Yeah, so layer feature 15, you get a complete.
So why is it that layer 1 is only a small
Layer 1
image?
is giving such a small
Because
image.
we are like
layer-
stacking
So what happens?
the dimensions of the matrix increases.
Dimension of which matrix?
The kernel is only acting on a small portion of the image.
The later kernels will encode more information of the whole image.
Why?
Because
Okay, what's the definition of a receptive field?
Where like which part of the image a kernel can
Which part of an image affects the kernel's output? That is the definition of a receptive field. So when you say a local receptive field, that means only those. Yeah. So now what happens when you have multiple layers of kernels stacked one on top of each other? The receptive field increases. So if you are gradient ascending back, initially this one kernel is affecting only those 9 pixels. When you have 2, it is affecting a 5 cross 5. With 15, it is affecting. Yeah. Okay. Sorry. No tote back.
Yeah, right. So
then this, which was this idea? This was that BGG idea, right? You can stack. Yeah, you can stack and increase the receptive field. That is exactly what you're saying.
Yeah, so we are going to take only the first layer. First layer will be this, the central kernel. So it will visualize this part. But if we are taking second layer, what it will be visualizing is what the first layer has created. First layer would have created something like this like all entire this field would have been taken into account for and this would have been represented in that one kernel's output. So that's why we are having a larger. And as we go deeper, eventually the final layers kernels have access to kind of the entire information. So they can update the entire thing using variables, right?
Show the distant layers on it.
Yeah.
So more opportunities for code cards. So not a code cards.
Right.
So so yeah, you guys can ask. There are a lot of questions. Answer any one of them, you get code cards. So where is Okay, so now question. You are starting from the center and you are taking some later layer. Why are you getting multiple eyes?
Because each picture has an eye in some other place.
Each picture has an eye in some other place. That is correct.
So follow-up question then.
No. Let's go.
Then is if there are eyes in different places in a picture, then how by the end of the last layer is it all coming into that one layer?
It learns to find eyes in all the places inside all the sides of the image by.
So okay, that is roughly the right answer. Which property of the CNN is like this referring to? Translational equivariance. As in the feature maps are same, the feature map that you get is same whether the eye is here or eye is here or eye is here. So when you gradient descent back, right, you get eyes. Now, question. Okay. Why only 6 eyes? It is equivalent. If I move by 1 pixel also, you get different feature.
Because if you have too many eyes, then the convolution layer cannot, the convolutions can't.
No, that is not the thing. The convolution layer is learning to detect the eye irrespective of where
it
it
can
is.
only detect something as an eye if it has like a particular size if it's big enough?
Yeah, size is fine. Size is fine, shape is fine. But the eye is here and moved by 1 pixel, still the model classified as an eye. So it is capable of identifying wherever it is. Okay. Why is it that when we do the
In the training data, most of them were imposed.
no, training data was very random. That is possible. That is one possible reason. You can take one, but that's not the entire reason. Kernel size is there, but it's not just kernel size. Can you tell me what the big reason is? Can you guess?
We're finding a local minimum while optimizing. So if we run it multiple times, you can find other eyes in different.
You can find eyes in other places, but why am I not seeing eyes in every place? Why am I not seeing eye?
Because it has learned to detect like only a few eyes. If it sees.
No, that is not right. When I'm optimizing, I will optimize all the inputs such that I get maximum output. So the image that will actually maximize my task is if I have eyes everywhere.
But in the training data, there's no image with eyes everywhere, right?
That doesn't matter. So
when it learns eyes as well as the surrounding.
But that kernel is okay. Fine. See, think about it. That kernel is so. What is it getting? It's getting output of edge detectors. Edge detectors are somehow getting converted into circles. Circles are finally being converted into eyes. So that kernel is an eye detector. Now this eye detector's output will be maximized if I have eyes everywhere, right?
Are we passing a local maximum for 6 eyes?
Am I passing local maxima for 6 eyes? No. So think about. So are we doing just gradient ascent, or are we doing something else? Are we just trying to maximize the output of the kernel, or are we doing something else also?
Regularization. We are like optimizing for lower.
Yeah, we are also so we are doing regularization. Correct answer. Which so you do 3 types of regularizations, right? Do you remember?
I do.
Oh, you haven't done it. Shit. Okay, sorry. Okay. Go ahead. Okay, wait. Let him. The question is still open.
Regularization.
You talk about the regularization. Then.
So yeah, fine. For now, this is the deep cleaning that I said. Google came up with this, and it uses layer visualization. So again, now when we talk about the entire layer, and the interesting part is instead of starting with randomness, they start with a particular image. Now this image will have some activation in that layer, right? So say in that layer there is a very slight detection of say cow or some dog. Say very slight. So there are some shapes that you can see. Oh, this is the face, this is the body, something. Just like we see shapes in the clouds. So if we, so even if some slight activations are detected of a particular feature, a particular concept that is represented in that layer, this optimization will enhance that feature. An enhanced feature will optimize it even further, so it will get even more enhanced. And this is by 10 iterations you get something like this, and by 50 iterations you get something like this from generation.
So if in case you had one of the kernels detecting a dog, by some reason it saw something in this jellyfish picture and thought it was a dog, and you are doing gradient ascent to maximize that output.
Yeah, now
that
it back
dog
question.
put dog everywhere.
Now it went back question. Why are always dogs and some animals only coming from? Why nothing else?
Because they're more in the training data. Okay, and that is the exact answer. Because in ImageNet, how many classes did ImageNet have? 1000 classes. Okay, in that 120 were dogs, different breeds of dogs.
Labrador, golden retriever, German shepherd. So like the model has to learn dogs better than other things, and that's why not overfitting. But like it has to learn to distinguish between dogs also. So it needs to learn these fur, eyes and all at a very early stage, because later it needs to learn features that are distinguishing between all of these, like pointed ears, floppy ears, something like that. So that's why it has to learn these features very nicely, and that's why mostly like we are randomly activating features, right? So randomly, usually these features get activated. So yeah, this was deep read. Now, an interesting point. So now we said, okay, this kernel, so there are multiple kernels. Say this kernel gives me some output. Another kernel gives me, I shouldn't say output. Say this kernel gives me some visualization. Another kernel gives me some other visualization. When I say it is giving me a visualization, when I am optimizing to maximize the output of that kernel, I am getting different optimal input images. Now say I am modifying my loss function. Now I am making my loss function as the sum of the output of these two neurons, these two kernels. In that case, what will the model try to do? It will try to maximize the activation of both of these features, both of these neurons. So you get some combination of neurons like this. And in fact, like when we actually do the follow-up class, everything is going to get added. So in fact, more than the features themselves, their combinations are going to impact our predictions. Right, so this is just a single example. You can see over here. So say this is some grainy structure and this is some pattern. When both of them are optimized together, you get something like this, the grainy pattern. Right. You have some football, you have something like this, and now you get footballs inside these designs. You have something like this. Okay, this time football is not doing much. Fine. So I have birds over here. You get birds' beaks in this shape. So you can see the feathers are in that texture. Right. So this is just combining multiple neurons to get a visualization of a better neuron. And why just add? You can take a linear combination. So you have, this is one feature, this is another feature. Now if you optimize, if your objective is only output of this feature, you get this. If it is only this feature, you get this. Now you can have a combination of them. So 0.2 times this, 0.2 times that image plus 0.8 times this image, this neuron. When optimizing this objective, you will get something like this. So you get kind of a smooth transition from one neuron to another. Now, okay. Next. So yeah. So now coming to realities. Reality is this. You start over there, step 32 over there, step 128 over there. You see, okay, by 2014, you are able to see like there are some flowers over here, some bulgy kind of thing over there, and but eventually you are not getting a clear feature, right? So what will you do? Even after 2048 epochs, you do not get a good thing. So increase the learning rate. Okay, fine. You saw it. Yeah, so I will increase the learning rate. And what do you see? Yes, and it gets bad due to the same reason as what happens over here. Like the learning rate is too that we just start oscillating. We need it to be just right, so that slowly we get.
Not my question. If you have large learning rate, can you escape the minimum?
Yes. Yes.
Maybe eventually land in a minimum after a long.
So how many of you say that irrespective of how high the learning rate, even if like it's x square, convex function,
It's a global minimum.
is global minima x square, only one minima is there. Okay. How many of you say irrespective of learning rate, I will reach the minimum? How many of you say if learning rate is too high, it will escape the minimum?
Like it will never reach.
Okay.
Never even.
Who can give me an explanation for that?
So if the by derivative in the example of x square,
Yeah.
we mean the tangent.
Yeah.
So suppose we take the learning rate such that, like suppose we are at a particular x naught. Suppose we set our learning rate such that it takes us to minus like 2x naught, for example. then when if we keep repeating the cycle, then you just get farther and further away from the.
Correct. That is the correct answer. So, yeah. So you can.
Example was this one that I gave earlier. So if x is equal to 1, you take your learning rate to be equal to 1. When you are over here, the gradient is 2, so you go minus 2, so you get over here minus 1. Here the learning rate is, because learning rate is 1. Here the gradient is minus 2, you go plus 2, you get over 1. And you keep on oscillating. So you will never get.
So if you take an even bigger learning rate, you will go up.
If you take a bigger learning rate, from here you will go over here, then over here. Fine. So the problem is, and you can see the problem everywhere. So say here is, say a football or something. Like you are not getting good feature.
So is there a way to, without doing the experiment, without samples, base a learning rate and
Okay, that goes into a different field. If you have a well-defined objective function, like well-defined in the sense, say you know that your objective is a quadratic function. There are upper bounds to, like mathematical upper bounds to what learning rate will guarantee you.
Yeah, not just quadratic. If it's like strictly convex, you can make a claim about your learning rate should, like the largest learning rate I can have, you can find from the.
So you need some information about the loss function or something.
You need information about the loss function, yes, about your objective function. So if it's strictly convex, if you are optimizing a strictly convex function, you can tell exactly what the optimal learning rate should be. But if it's not strictly convex, you can't really say that.
So yeah, so this is not working. So now, and yeah, even after lots of epochs, like 2048 is anyways a large epoch. It's not good. So if this is happening, how did you get such good, nice looking patterns that I showed you till now? So that's because of the power of regularization. So what we want, if we can state that very clearly in a loss function, we can overcome this problem. So how we do that? Right. So what we want is, so we want that in my final. Okay. So say this is my input. This is the x that I am trying to optimize. I want to find this good value of good x. What do I mean by it's very bad or it's very blurry? Oh, not blurry. It has noise. What do I mean by that? I mean to say that the difference between every pixel, the difference of every pixel with its neighboring is very high. Like it's abnormal. If this pixel is red, the next pixel orange is fine, but next pixel directly blue is weird. You don't want this. So you want to minimize the difference between the colors, the values of two neighboring neurons, two neighboring pixels, right? And every two neighboring pixels possible. So what we do is, and not just their difference, their difference squared, because okay, first of all we want the mod of the difference. The positive negative does not matter. I don't want this to happen. So I want to minimize something like, so say I want to minimize the difference between this. Say this is A1, A2, A3, A4. I want to minimize A1 minus A2 whole square plus A1 minus A3 whole square plus A2 minus A4 whole square plus what's the meaning? A3 minus A4 whole square. Right, I want to minimize this. All possible combinations. Or you can state this very simply as just take this image, move it to right by 1 pixel, subtract and square it, and add all of those terms. So you will get terms like this minus this whole square, this minus this whole square, this minus this whole square, this minus this whole square. right, and some those terms. Then take the image, move it 1 pixel lower, take difference, square, and add. So you will get differences like this one is whole square, this one is whole square. Right, so all neighboring pixels, all these variations are included in our regularization term. And when we apply this regularization, the kind of this noise that we are getting reduces. So over here, let's take this here. So you can see it has a lot of noise. Now this is the total variation or smoothing. So this is the variation. So variation is again the difference between two neighboring pixels whole square. And so again, when I am adding another term, I will scale that term and add it. Just like we had lambda into something, we also will add a weighted version of this to our loss function. That weight is what I am controlling over here. So I am putting say 0.1. And let's synthesize features. Is it smoother? Like it's slightly smoother. Okay, so the reason is our net is trained only on CIFAR 10. For understanding CIFAR 10, you actually don't need to understand everything about how images are created and all. So
like CIFAR 10 is a 32 cross 32 image. It's
okay,
so a cat is so a car is only like 10 pixels wide, 1 pixel is all. It doesn't need to learn what a door or a wheel or anything is to learn what a car is. So your car detector is probably something much simpler than what you have in ImageNet, where ImageNet is like 226 cross 226. So you kind of need to learn what a wheel looks like to predict a car. In CIFAR 10 is just such different classes, you kind of don't have to do that. But now coming back to, yes, my doubt back question. Why did you see only 4 eyes? Yeah, why did you see only 4 eyes?
Like, so this has more noise than the previous one which I did with slightly more noise.
Okay, you don't get why you saw only 4 eyes and not eyes everywhere.
Like when we shift the image one down and one left, and then we're trying to like we want to incentivize
these images that we're seeing here same as the eye examples.
Yeah, so it's the technique of generation is the same. The model that you're using is different. They trained on ImageNet, we trained on CIFAR 10, so that's the issue. But the approach is the same.
So that image is like what the model is looking for when it's doing image classification.
Yes, what that kernel is looking for. So now the question once again remains: why didn't you see I and this
Because of the receptive noise.
Huh?
Is it because of receptive field? Because if like suppose the final image which it generates for what it's looking for has eyes everywhere, then individual pixels and fields lose their value. Because you're creating.
I mean, like you could have like with some transparency so that they still look like eyes. Yes, it is that regularization term. So you have two competing terms, right? You have one term that's trying to maximize the kernel's value, and then you have the regularization term that's trying to minimize this, effect of overlapping images, because you're taking this image and the same image shifted by one and you're subtracting that. So you're trying to minimize the chances of it predicting I explicitly. You're like, that's literally hard coded into the loss function.
Yeah. Another thing is there are multiple kinds of regularization functions. So if you actually look at that paper, it gives, these all different people have given different kinds of regularization functions. Uses jitter, it kind of uses the dataset example somehow. So we won't explore all of them. Like this one is enough, I think. Yeah, and coming to this invariance, the thing that we had talked about, like in the very first thing, using a simple neural network does not work, because neural network is not space invariant. Like if you move it, if there is a translation from say you move by 4 pixels or something, the activations will change entirely. So this is to show that This is the feature now. Now see, you shift it by 1 pixel. You see almost no change in the feature now. So this is the feature now that you get after the end of last convolution layer for this image, this bird image. And yeah, for 4 pixels, okay, it moved a bit, obviously because 4 pixels is quite something, but again the basic design is the same. Very good. Yes, this was just one thing. Yeah, you can compare the cosine similarity between these two images. It's 0.82, so it's very good. Right. So now coming to more perks of regularization. So there was some neuron. So layer mixed for the neuron number 55 in Google. Doing a simple optimization over there gave you this. So you can see something like cat head, a fox head, and like cars or something. So it probably means that the kernel is attending to multiple things, multiple maybe similar looking to it. It is finding them similar. But if we do a simple optimization, you get something like this. So what we can do is, we can say, okay, I will modify the loss function. This time I will modify the loss function entirely. Objective function. So I will maximize. Instead of just saying that give me some x which gives you the maximum activation AI, I will say give me x1, x2, x3, x4, 4 images which will all give me like the sum of AI over here, AI1, here AI2, AI3, AI4. Sum of all of these should be maximum. So what does that mean? This should also give me a good activation of this feature A1, feature AI. This image should also give me a good activation of the feature AI. All of these images should give me a good, like a high activation of that feature AI. So if we train this, so you got it right. So the loss function will be sum of all of these objective functions. Is this enough, or do we need something else?
Can't all the x's be the same.
Exactly. Right. So if we just do it this way, everything can be the same. So it will say, okay, this image is giving me a very high activation. I'll put this same image everywhere. So we will add an additional regularization term, which is x1 minus x2. Say I take their difference squared, or maybe I can take cosine similarity also. For now, let's take this. Plus x2 minus x1 square. In fact, all the possible combinations, all pairwise combinations of these terms, I will subtract from my loss function, from my objective function. So if these are being subtracted from my objective function, what my gradient descent will try to do is maximize this activation and minimize these terms, because these are getting subtracted from the objective. We want to maximize the objective. So try to minimize. Wait, sorry. Then I'll add these terms. So it will try to maximize this also. So it will try to maximize. What is this? This is the difference between x1 and x2. So it will try to maximize the distance between this image and this image, this image and this image, this image and this image. All pairwise combination distances, it will try to maximize together as a regularization. Was that clear?
Did everyone catch it?
I was a bit wavy.
Any doubts? What is the goal of this particular thing?
To ensure maximum.
Like one neuron could be, so if you look at this, you see car and you see fox. So now you wanted to see, oh, maybe one neuron is actually not just detecting one thing, it's detecting helping to detect multiple things. How do I know what all things it's helping to detect? I suppose start with 4 images, and I ensure that each of those individual images are as different to each other as possible, and individually have maximum activation as possible. Make sense?
So during training, all 4 are fed at the same time.
What?
Yeah, all 4 are made at the same time.
You just add all those steps.
And so, like, I just want to show you the power of controlling the objective function. So, you have the mechanism which will optimize any loss function that you give. Just make a good objective function. Yeah, so this is something, say balls, so it is detecting different kinds of balls. Football, so it has a leg also, so because football is usually associated with legs. There are some kind of balls, there are smaller balls. Yeah, this one. So this one, if we looked at it in isolation, we would think, okay, it detects some eye and semicircular thing. But if we do it with diversity, we see, okay, even if it is not curved, or even if it is not curved downwards, you get similar kinds of things. So it is detecting all of these. You get a better understanding of what that neuron is doing.
Yes,
Yeah, I wanted to know about like the color scheme of all of these images that get generated. Like it's kind of like all the kind of like repeated like eyes like that. They just have like random colors like put into it. There's no association with like an outline and the color. Like say for example in this set, all the training data set was of that like orange, brownish, yellowish color. So all generated images are of that color. Right? And when you had like a training data set of like a lot of colors, then the all images that were generated had like colors just randomly spread out all over.
I think when you're starting from noise, you get some random colors. If you're starting from some particular image, you get some particular colors.
The
But no,
football
but,
example.
okay.
If you get the same color, it just means that that kernel is specifically looking for that colored features.
Can you go to the football example once?
See, it's also possible that this is one of the local minimas. So if you regenerate it, I think you might get different colors.
Yes, because it reacts to tennis balls also.
Yeah, the tennis ball's color circle just keeps getting randomly generated in those first 4 places. They're like, but there is no tennis ball there. It's like colors.
So if you think about, you see that this kernel is getting activated whenever there are balls or whatever. Right? Now in first layer, what are the kind of features that will give access to a ball? Is probably some kind of edge detector, maybe some kind of color detector also, maybe like green and white are particularly well represented for balls. So then when you do gradient descent, that impact is coming. Okay. Maybe it could be that.
Right, so yeah, just some more examples of that. Yeah, and we'll move on quickly. So yeah, now coming to attribution. So till now, what we were asking is, what input will make this this feature activated? What input will activate this kernel or this neuron? Now let's answer the question. Let's ask the question: what is this kernel's output going to do to the final output? So say finally I am going to predict a tiger cat. How is this neuron's activation influencing that? So obviously, so say you have an image of a dog and grass all around it. So there might be some neurons which would be activated to grass. Activated in the sense they will give a very high activation in the feature map. How is this going to help or not help the final prediction that this is a dog? So over here, so let's see it with an example.
Did you guys get the problem? So if you give a picture of a dog sitting on grass, you will have some neurons that are grass detectors, some neurons that are dog detectors, and some neurons which are whatever other cat detector. So now, and if the final class is a dog, which of these neurons is actually contributing to the final label prediction? Is the question. Okay. So you're looking at downstream effects. So till now you're looking at inputs, now you're looking at the downstream effects of that kernel. Okay? Clear?
Yeah, so these are the multiple layers. This is 3A, 4A, 4D, 5A, like in order only. So what we can do is we want to identify so what we will do is we will find the gradient of the final class logit. So let's call that class logit as C. Gradient of that class logit with respect to my whatever kernel this is. Let's call it kernel A. This gradient is going to tell us how did this kernel, like if this kernel was so again, now this time we are looking at it completely independent of the what input was there, right? This is just the kernel, which is a part of a model. So I am looking at the derivative with the gradient of my class logit with respect to that kernel. This tells me if this kernel was activated, what, like how much it would have affected the final logit. And I take its dot product with the actual activation that I had over there. So let's call this kernel A, activation A. So you take the dot product of these. So identify, the activation A, so consider for now they are in some directions. So this is the gradient direction. So this shows that this kernel is going to activate the class. And if your input vector is say perpendicular to it, their dot product will be 0. So it means that it is not going to activate the activation, the contribution of this activation, this kernel for the final class prediction is going to be negligible. But if this feature map is also, the activation map is also in the same direction, it means that activation map agreed with what the kernel was trying to go in the direction of, and we got that class prediction. Like we got a good contribution from over here for the class prediction.
Did everyone catch the idea?
What's the activation map?
So activation map is your feature map, as in you passed it through 5 layers of the model, whatever feature map, say 32 cross 128, that box is your, that cube is your activation. Okay, your image is output, the output of your filtered.
Right, so say these are multiple layers, and now say I want to say how Labrador retriever was affected. So these are the kernels that affected this Labrador retriever.
So the first term is telling you how much
Say
the
again,
change in the kernel will affect the output, and second one is telling you how close the filtered image is actually to that change in output. So if that kernel is affecting the output a lot, but the kernel, so think of it, you have two terms. You have two important things. You have direction and magnitude, right? So if this is affecting the output a lot, then still this will activate strongly. If activation at a particular layer, approximately same norms you can assume. Okay, and if the angles are same, then that means whatever change the kernel is affecting on the final output, that same change is what the activation is also showing. Okay, so that is why it's giving it.
Right,
So that way you get a way to select out parts.
So these were the so we take the entire layers visualizations on these small patches, and we have, so the original image was this was the original image, and what we did was we replaced each patch with the visualization of that layer at that patch. So you can see as we go along this, the size of this patch is increasing because the local receptor field is increasing. And this when we scale with their activation magnitudes, we get these plots, and these plots are what are getting compared over here. So when I am saying that these parts are contributing for the Labrador Retriever, it means this entire layer on this part of the previous feature map is giving a feature map which has contributed for the Labrador Retriever prediction. And you can even see over here. So say I want to see if this is the feature over here, this is the neuron over here. It is influenced by this. So
Influence by thing on the left.
I think they are going in the gradient descent direction.
Labeling is a bit.
So like because of, so again you take gradient, so now instead of taking gradient of the class output with respect to this feature map, you will take the gradient of this feature map with respect to this kernel, and you will get this. So these are the kernels which allowed this to get activated and so on. So we are running out of time. Yeah, and then we can get something like circuits. So something like this. So what all helped to predict it as a tiger cat? So it was not predicted tiger cat, and that's why you can see this is a dog face activation. And where was this activation found? On these places. Where was this activation found? Over the heads. So this is the kind of head kernel. And these are some neurons. These are some neurons in the next layer. So these two neurons, so red color means negative influence. So these did a lot of negative influence over this snout kernel. Snout kernel, and together both of these did a very negative influence to tiger cat. So this negative means that the vector is in the entirely opposite direction. So you are getting negative influences. They are trying to remove that class. So that's why you did not get a tiger cat, and they are increasing the activation of Labrador Retriever. It's increasing the logits of Labrador Retriever. Sorry for my terms. Yeah, that was about attribution. Now coming to activation atlas. So the big idea is I have many kernels. All of those kernels. So even in a single layer, I have so many kernels. If I want, I can go and visualize each of them manually. But obviously that's not what I'm going to do, because there are so many, I can't see all of them together. So I want something like good visualization, something like I see this and I see, oh, this is the entire thing that this layer is doing. So that's where the idea of activation atlas came. So what is activation atlas? So you first collect activations. So activations are activation maps, the outputs that you get after every kernel. So you collect activations from the entire ImageNet dataset. From entire ImageNet dataset, you take a random batch and find its activation. You get all of these activations. So these are usually 32 cross 32. So 5 and 2 dimensional vectors. Now there is something called dimensionality reduction. So PCA is an example of one of them. So what happens is, if you have, say, 3-dimensional vectors and you want to visualize them in 2 dimensions, what you do is you project them on a 2D surface. But now you can project them in multiple ways. Like project in the sense you just look from this angle. So you can look from this angle also, this angle also. So which angle do you choose? So there are some techniques which give you a good angle to view from.
Okay, come back. Okay. You have in 3D space, you have one ball here and you have one ball here. Okay. I want to draw a plane such that if I project these 3D vectors onto that plane, I will see these two balls as separated as possible. Okay, that's my question. Did everyone follow the thing? Imagine that I have one ball here. Imagine that I have another ball here. Okay. What should be the plane to draw such that I see the maximum separation between these two balls in in the projection. So do you know what a projection is? If you like shine light and look at the ground, however it looks is the projection. Okay?
Light is over the top.
Light, you can move the light. So you can move the light or you can move the plane, both are equivalent. No.
The plane passing through the ball.
Passing through the balls, more specifically?
Parallel to the line.
Huh?
Parallel to the line joining those two.
Parallel to the line joining those two.
Or
That's
running the balls with a line
Yeah.
and then take a gradient and the parallel.
That is true. That is exactly true. And why is that giving you maximum set? Okay, yeah, that's fine. That is a good enough answer. So how many people answered? I don't have it. That's like too many. I have only one answer. Okay. And which will give you minimum?
The perpendicular bicycle.
That would be too easy. Okay.
Wait,
you can check
perpendicular. So yeah. So there are similarly. So this was an example of a linear reduction technique. You can have non-linear reduction. So something like both of the two balls over here will come together and look like this. So in short, it's like a non-linear transformation. What we saw now was projecting them linearly. Those who are into linearity might know this. This is projecting linearly when we are doing light, we are showing light or something like that. But we can do non-linear transformation. So there is something called a U-map, which is a dimensionality reduction technique. So if you have multiple vectors, high dimensional vectors all scattered around, you can project them in 2D such that they look neat, kind of. So this is the U-map used. So we project all those activations over here, so you get something like this. Right, and now you can see somewhere it is very sparse, somewhere it is very dense, and so on. Obviously, the near point. So the idea of dimensionality reduction itself is if there are two vectors which are near, even in the projection they should be near. Otherwise, there's no use of this. You can just randomly place everything in the grid. So if you see, so if there are two photos of a dog, their activations will probably be together, and something different will be entirely different. Now what we will do is now we can visualize every point. So we will allow some amount of approximationness. So we will make a grid around this, and at each grid. So if I get this grid, I will look at the average activation direction. Now, okay, so if I can, again, if I have an activation, activation in the sense I have a vector, like so. In that sense, I have a feature map. Activation is because I'm stretching this out into a single vector. I can find input such that it gives me a feature map whose dot product with this is the maximum. So now I'm just saying that I will change my objective function. Now my objective function will be the cosine similarity between the feature map that my input gives and the activation map that I have over here. And I will do backpropagation, feature visualization. I will get some image that I will put at that position. And so on, I will fill the entire possible map that I have. And as an additional tweak of visualization, wherever it is sparse, I will put a shorter image, like a smaller image. Wherever it is dense, I will put a bigger image. And what I will get is an activation atlas. So first, you agree that all points in the data set are somewhere over here.
Did you understand that?
So all kinds of images possible, dogs, cats, everything are there somewhere over here. And second thing is they are grouped by similarity. And we are visualizing each of them. So we are in effect visualizing over the entire ImageNet data set whatever the model has learned. Whatever features the model has learned over the entire ImageNet data set. And yeah, let's look at it more closely. So this is the activation atlas that you get, and you can do it for each layer. So for all different layers, you get different atlases. Overlapping in the sense? No, I said that we project them first, and then so there might be multiple points at a position. I will draw one grid. Like I will draw a grid, and if there are multiple points in a box, in a cell, I will take their average and do the optimization. Because I have to stop somewhere, I can't visualize all the features for the 1 million, however many millions of imaginary points. Right, and now you can see all of these. So say this is somewhere fruits, this is kind of the fruit part. So yeah, the labels are from these points. So when we were making those points, they came from some images, right? So we can just write that label to our grid cell. So are the labels visible? So you have banana over here. So now why is banana looking like this? Because it's probably a fruit space, a cell for fruits. But yeah, banana was the
If you look at the probabilities, banana, spaghetti squash, butternut squash are all the same. So some combination of.
And yeah, then you look at golf balls. So now slowly fruits are becoming balls, golf balls, ping pong ball, wooden spoon. Yeah. Yeah. So this is what we get. Data and yes, we got this. So fine. So this is what. So now we can either make 20 cross 20 grids. Like that grid is our wish. If we make it larger, we will be able to visualize lesser features, but more clearly. If we make it smaller, we will be able to visualize deeper features, but like we'll have to literally zoom in and look at everything. So yeah, we have animals over here. Then slowly moving to reptiles like Indian cobra, snakes, and all. Then slowly moving to some machines, cocktail, water jug, cup, petri dish, dog also somewhere over here, loudspeaker, maraca, plastic bag. Now we move on to clothes like sleeping bag, jersey, oxygen mask, stretcher. Yeah, and then we move on to body parts like band-aid, bathing cap, bow tie, like that. So yeah, let's explore this. So yeah, so we can see at the top we have all these animals. Then we slowly move on to their body, fur of animals, body parts, backs of four legs animals. Then we find animal legs like moving below. So you can see over here, we are starting from the top, moving below. Even below we can see ground, like now there are feet of different animals. Then moving further below we find grounds. So cliff, mongoose, sandbar, doormat, French building, kind of and even move down, so we get water bodies. Then on the other corner of Atlas you have written things, so websites, book jacket, packet. Moving further up you get this we saw. Then in the center we have these fruits and all. And yeah, now because this is, as I said, it was a non-linear projection, right? So there is no necessity for relations between those features to be in a straight line or anything. So you can go from here to here. So it's kind of a curve, and you can see that you are moving from many fruits to a single fruit. And similarly, from many people in a crowd to a single person in a crowd. When we move from here to here. And similarly, when we move from over here to here in a curved way, you can see water is slowly going to beaches and then becoming rocky cliffs and all. Similarly, greenery we can see from clear images to blurry images. like these paths can be non-linear because we have projected them in a non-linear. And yeah, now comparing layers, the first layer might have something like simple, just green color. Then we have features for leaves exactly, and then in further layers we have features for specifically cucumber, cabbage, capsicum, and so on. Right. Now, okay, fine. It's just a brief description of what we found. Yeah, we can. And one thing is, in later parts we find special peninsulas for each of these different things. So initially, what is just summarized over here. In later layers, so later layers are obviously looking at more deeper features than the previous ones. So as we go ahead, we get say, so here we had only one peninsula, here we got two peninsulas. So differentiate
Does that
between.
make sense? Does the idea of peninsulas
Become more specialized in some.
Because I mean, like, you can see a lot of animals will have eyes, but not many animals are dogs. So that makes sense that you start seeing specialization as the layers go.
Yeah, so that's it for today. In fact, there are, we will share these resources. So you're using this activation atlas, you can actually do something like adversarial attacks. So what that means is, this image if you give, it is going to classify it as a gray value. Because that's the correct answer, it's a gray value. But if you add the image of a baseball, it will suddenly start classifying it as a great white star. And later, so if you even make this bigger, it will start classifying it as completely different. Neither baseball nor great white star nor gray whale, something entirely different. And how can we control? So this is called adversarial example. So you always want to try and attack the network, like make some images such that the network will break down. It will start giving wrong output. So something of that sort we did over here. Adversarial attacks. So we uploaded the bird JPG, right? And initially it's fine. Now what we are doing is we are adding random noise to the entire image. So for now it's 0. Now I added 0.01 of this noise to this image. So obviously it might become noisy. This is not like there's some bug. This is not representative of that. But the image might become noisy. But now, what is the model predicting? It is still predicting class 2. Like it is still predicting it bird. So it's fine. Now as we move ahead, okay. But now I added 0.04 strength of that perturbation, and that random perturbation. Now if we see the image, due to some error it's not working. But if we see the image, it might have become completely like full of random noise, and because of that, the model changes its prediction from class 2 to class 0. So class 0 was star or something, right? So this is called adversarial attacks. And activation atlases, interestingly, provide us way to formalize this. So how do you know which image should you put over here? Like, should you put a baseball image or should you put a grass image? What image will you put over here to convince the model that this is something else? That explanation we get in using activation atlases. So you can read it later. We will share the resources.
And an interesting thing is this perturbation noise that you add. You can also, like, there has been work that shows that you can change one particular pixel, just one pixel in the entire image, and still get it to fail. So you did all this work, and you spent all this time making big model, and you trained it for classification, and then someone comes along and changes one pixel, and now your model is successful. Okay, so anyway, this whole event, entire series was sponsored by JST. That's all the tote bags you're getting, all the refreshments you're getting. Extremely grateful to them. Please scan the link. They have a bunch of training videos and games that they love to play and all of that. We'll share that message once again so you can get those resources on the group, right? On top of that, we are organizing another hackathon with J Street, which is very cool and quite non-standard from your generic hackathon. So all of you please register for that. Tell all your friends also because it's quite non-standard hackathon. Everyone scan? Okay.
So
about all the opportunities that Jane Street is coming up with next few years. Like you will get your mates through your like whatever you register, you get the mates.
So, is everyone ready for like 1 30-second quick recap again? The whole thing. We started. What was the first idea? Lead idea was convolution. Dynamic convolution. Second idea? AlexNet reason? Scale. Big model is better. Third idea? VGG. What is the start convolution? Bigger, larger receptor fields. Fourth idea? ResNet. Why ResNet? When you kept increasing the depth, you plateaued, so you added skip correction so the gradients can propagate. Next idea? VIT. Why VIT? Okay. Swing transformer. What swing transformer? Patches windows. Why patches windows? Localized detection and reducing computational cost. Convext. What is convext?
Addition of resonant.
Yeah, take whatever transformers architecture was, map a convolution as close to that as possible. Then what do machines see is all the activation analysis, and at the end you can attack these models and get no accuracy. So thank you all for attending. It was really awesome. Also one more thing. This is that deep dream image, and that very corny joke on the group is why you shouldn't get high on drugs, because you are quite literally getting, your neurons are getting high. Feedback. Oh, awesome. Yeah. Please give feedback for yeah, we'll put the hackathon link on the group.